Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of vibration. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? And the question number four, how to learn the knowledge from this course. All right. So let me start with the review about the answer to the first common question that you may have in mind. This first question is about the why to study this course. By now, you should know that our mission on Earth include number one, to understand the world. Number two, to improve or change the world, right? Then how to understand the world? The answer is to have sensory data. Then how to obtain sensory data? The answer is to make use of a measurement and the sensing system. Once we have the sensory data, then we should be able to discover knowledge, because the sensory data is the necessary input to the process of discovering knowledge in the physical world, right? Then how to improve or change the world? The answer is to invent smart machines, smart products, smart system. Then how to invent these smart products, smart machines, smart system? The answer is to incorporate closed loop feedback control system. Then what is a closed loop feedback control system? Basically, it is a system which consists of three basic building modules or three basic building blocks. One of them is a sensor. Therefore, the study of a measurement and the sensing system is extremely important, okay, to the design of a future smart system, smart product, and smart machine, etc. Right? And from this slide, you see even in future, in the city environment, there is a need to have a smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, and the smart healthcare system, right? And also you see the need of deployment of Internet of Things. And inside the Internet of Things, you understand that one of the two major devices is a sensor, right? Or networked sensor. So therefore, the study of this course is extremely important, not only in industry, but also in society, right? Then the second common question that you may have in mind is about how to study this course, right? My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask yourself these four questions: who are the user? What are the needs of the user? What are the functionality of the product or system that you are going to develop in order to meet the need of this user? Then what should be the solution behind the design of your future product or your future system? All right. Then answer to question number one should be straightforward to you, because this user include human being and the smart machine, smart product, and the smart system. All right. Then what should be the need from this user? The need are the same. Basically, is to obtain sensory data. Right. Then what should be the functionality of your future product or future system, such as sensor, measurement and sensing system, or Internet of a Sensor or Internet of a Things, okay, which could meet the need of this user. The answer to this question depends on the specific nature of user. For example, vehicle may need a certain type of a sensor, robot may need another type of a sensor. All right. Then answer to question number 4 is to study well this course. All right. At the end of the study of this course, you will know the answer. All right. Okay. Then the common question number 3 that you may have in mind is about what are you going to learn from this course. Basically, this course will cover the physical principle behind the design of a popular sensor in electric domain, in magnetic domain, in environmental system, and in intelligent system. All right. In addition, this course will teach you the basic detail about the physical world and the basic detail about the conceptual world. And also, this course will teach you the basic knowledge for you to cope with randomness in the physical world and for you to understand the fuzziness in the conceptual world. All right. Then the question number 4 that you may have in mind is about how to learn the knowledge from this course. Basically, you can apply the learned knowledge to guide the design of a sensor or measurement and the sensing system. All right. The design basically involves 2 steps. Step number 1 is to transform the physical quantity into readable value. All right. Then in this case, we can proceed with step 2. Step 2 is to calibrate the measurement and the sensing system so that the output from your sensor or your measurement and the sensing system is exactly equal to the value of physical quantity on the measurement and the input. In addition, after calibration, then you can assign unit of a measurement to the output of your sensor or your measurement and the sensing system. And this unit of a measurement is exactly equal to the unit of a measurement of the physical quantity on the measurement. All right. And for step 1, basically you may face 2 situations. Okay. The first situation corresponds to the case in which it is good enough for you to just use front-end sensing element to convert the value of a physical quantity on the measurement into readable value. All right. However, in most cases, you may want to apply or you may have to apply, the combination of front-end sensing element together with back-end sensing element in order to transform the value of a physical quantity on the measurement into readable value, right? So this slide basically summarizes the general guideline for you to follow in order to learn the knowledge from this course, right? Okay, now we are ready to enter the study of today's lecture. Today is about the measurement of a vibration, right? And the vibration is not like a physical quantity such as a voltage, current, and the vibration is also not like a device such as a resistor, capacitor. Vibration basically refers to the dynamic response from solid, gas, or liquid, right? So, and we can use a signal or time function to represent, the dynamic response from solid, gas, and the liquid. However, for vibration, it is a special type of response from solid, gas, and the liquid. And this response behave like a periodic function. And in the ideal case, we can use a sine function or single sine function to represent a single source of a vibration, right? Then in general, we understand that the vibration system is an MIMO system. So this is a technical term in control theory. MIMO means multiple input, multiple output, right? And here you see a typical example. I guess all of you have had the experience of riding buses in a city. I don't believe that we still have a student who do not know what is a bus, right? So when you ride the bus, actually you feel you experience a vibration, produced by the bus, and there are many source of vibration, okay, inside the bus, which could produce vibration. For example, each wheel has a suspension system, and the suspension system basically it is a source of vibration, right? And in addition, a bus has an engine, John. When the engine rotates, so it is also a source of vibration. So therefore, immediately you understand, okay? So bus is a system or is a vibration system with a multiple input and the multiple output, because you can move around inside the bus everywhere, you will feel vibration, right? So this is a dynamic phenomenon or dynamic response like that. Every one of you should be familiar with, okay? So you should not say that I don't believe any one of you who did not take, okay, any bus or any vehicle or any car or any train, okay, and eventually an airplane. When the airplane fly in the air, okay, sometimes you will feel vibration in the air. All right, okay. So I hope, okay, you will feel comfortable about the study of this lecture. And since vibration is a response, okay, it's not like a resistor, capacitor, we have a property, all right? Then here, basically, we talk about the transient response, all right? And we use a time function to represent this transient response. Therefore, we may face a special situation, okay, when we do calculation of vibration signal, and also it will be quite special when we undertake a measurement of a vibration signal, right? So this lecture may be slightly different from the previous lecture, right? Okay, so it is always good for us to understand the physics behind vibration and also the mathematics behind the vibration, right? So, and actually vibration is very useful, okay? It's not the noise being produced by rigid body, by air, or by liquid, etc. All right, because when you ride the bus, you may want to ride the bus without the vibration. Then you feel very comfortable, no vibration. Okay, but we can always try to design future bus with zero vibration. That could be a challenge for us to take. All right, to see how to achieve that result. All right. However, vibration is useful because we can make use of a vibration to implement actuator, to create rotary motion, to create linear motion, all right? And in addition, you know, this is Tesla. Nikola Tesla is one of the greatest inventor in the world and in the history of the world, all right? Then you see his statement. He says that in order to understand the physical world, we just need to focus on 3 keywords: energy, frequency, and the vibration. So that make you feel, okay, importance of this phenomenon of vibration, because at atomic level, actually you see what? Vibration of atom, okay, vibration of electron, all right, and the vibration of a molecule, right? So you see vibration is extremely important, okay? And when the photon travel in the air, so that is also a vibration, all right? And then the signal, vibration signal, basically is a pure sine function. So this helps you to understand the phenomenon of vibration, okay? Light basically is a vibration signal, right? So treat vibration in a broad sense, right? So, and this is why Nikola Tesla, okay, make such a statement. So you see the importance of vibration, which is at the same level as energy and frequency, right? So in industry, we may make use of a phenomenon of vibration to come out the design of actuator. And this video will show you one example. So you see, this is linear motion. Make use of vibration to produce a linear motion. And this is a rotary motion. you see the top disk rotate, okay, clockwise, you see. So from here, you see we can produce vibration, all right? But later on, we'll show you the working principle, okay? From voltage signal to periodic vibration, all right? Then this video show you the similar working principle for us to make use of vibration to design rotary motion, right? To design a rotary motion device, okay? Such as a rotary motor, right? So you see the vibration produces. Okay, so these are the example, all right? And another application in industry is to measure vibration signal, then analyze vibration signal in order to identify and wanted the source of a vibration, because this source of a vibration indicate the potential failure of motion machine, all right? So this is a very good source of information for us to prevent, okay, failure in motion machine, all right?
You can use vibration analysis alongside other technologies to get the earliest warning that that is beginning to occur, that the early stages of failure are occurring, which may end up like that if we don't do anything about it. And vibration analysis is a terrific tool for doing exactly that, because vibration analysis, in a sense, enables us to look inside the machine and see exactly what's going on, whether it's gearbox with bearings, you know, blowers and fans and so on. We want to be able to look at those bearings, look at the gears, look at the impellers and so on, and find out what's going on. You know, if we could look at that bearing and tell that it's lubricated properly, installed properly, there's no damage to the raceways, there's no damage to the rolling elements, then we have the confidence that we can go on producing our product and it's all good. But if we see something, then we can act. Same goes with gears, whether they're timing gears or inside a gearbox. Are they aligned? Are they lubricated? Is there damage to the teeth anywhere? You know, whatever the case may be, vibration analysis lets us look inside the machine. Now, in this case, we've got, you know, the motor driving a pump and a vibration sensor sitting up on top. Now, I'll explain a bit more about that in just a moment. But you may first imagine that, you know, all the vibration is transmitted along and goes up to this point, and maybe from this side as well. And that's one of the things I'll mention a bit more about in a moment, just where is the vibration coming from and how's it getting to that sensor. But one of the keys is that vibration analysis, in a sense, enables us to sort of listen. Well, what is happening with the shaft? What's happening with the bearings? What's happening with the rotor bars? Now, we pick up all those sounds from here. They all combine together into one measurement, but separating them in frequency and some of the other things we'll explain let us do that so we get an idea of the health of each of those components. Over this side, oh, that bearing is not in good condition. For the pump, we've got pump cavitation. On the machine head, not many machines sound like that, but anyway. Okay, so the way we do this is, as you've just seen, we can put the vibration sensor up there on the bearing, and all the vibration is transmitted, you know, through the machine itself up to that point. the sensor has to be mounted properly. That is very important, so that all those high and low frequencies get up into that sensor. But the fact is, when we mount it up on top, that is sensitive to the vertical motion. Whereas if I move it to the horizontal location, that's now much more sensitive to the horizontal motion. So, for example, if it was rocking back and forward due to looseness or resonance, then the horizontal measurement will tell us about that.
All right, so this video basically show you the scenario of making use of a vibration sensor in order to monitor the dynamic condition of a motion machine, all right? And in the society, in the industry, a lot of motion machines, like a car is a motion machine, an airplane is a motion machine, a power generator is a motion machine, a production line has a lot of motion machine, all right? And in the transportation, the ship, etc. All right. So this is a very, very important task, okay, for us to undertake. Then this task will be enabled with the use of vibration sensor. All right. And then in general, we can talk about the vibration due to solid, the vibration due to gas, vibration due to liquid. All right. Then for vibration due to solid, basically, we have at least two major causes behind the unwanted vibration. One is axial misalignment in transmission, another is radial uneven distribution of masses. And later on, I will show you example for you to understand. Okay, what do we mean by axial vibration? What do we mean by radial vibration, etc. All right. So in industry, and we may have some critical location which we do not want the failure to occur. Then we must monitor, okay, the dynamic working condition at least a critical point. All right. So now we are able to understand the definition of a vibration, because based on the video in the previous slide, then you may want to know what is vibration exactly. So now you should be able to understand the definition. Vibration basically means a periodic motion by liquid, by gas, or by solid, all right? And the vibration is a phenomenon of a dynamic response. Vibration is not a physical device like a resistor, capacitor, right? So vibration basically is a dynamic response from any dynamic system, all right? So, and it's a special response, okay? So it's a periodic signal, right? So, and in this slide, then you see we can produce vibration with a solid. Okay, this is a solid. We can also produce vibration in air. Air is a gas, okay? And some basically is a vibration signal, okay, of alternating pressure. And we will study vibration in air in a separate lecture. So here, the focus is on the measurement of vibration by solid. Okay, vibration in air will be studied in a separate lecture, right? So keep our focus on the study of a vibration by solid, right? And liquid may also cause okay, vibration, okay, which will demonstrate in the form of periodic displacement in the vertical direction, okay, in the water surface, etc. Right? And this slide basically show you typical scenario of a vibration in air. Then in this case, vibration correspond to alternating pressure in air, right? So you will see that this area has a lower pressure, then the dark area correspond to higher pressure. Then you have a concentration of air molecule, right? And in ideal case, okay, and now you see this is the ideal vibration signal. So we consider sine wave is the ideal vibration signal, right? Then all the other signals should be the combination of sine function, right? So this slide basically already convey this knowledge to you already, all right? Then this is a vibration in liquid, all right? So then vibration in this case refer to alternating, okay, displacement, okay, in the vertical direction, okay, on the water surface, all right? And then this video basically show you vibration due to the axial misalignment, okay? And we call this as axial vibration of a solid, okay? Then in this case, basically vibration refer to the alternating acceleration. So you accelerate upward, accelerate downward, accelerate upward, accelerate downward, all right? And here we do not use the term deceleration. So acceleration, if there's acceleration, could carry positive sign, negative sign. Then it is simpler for us just to stick to a single keyword. That means acceleration could be positive value or negative value, all right? But in layman terms, sometimes is to help non-technical people to understand, okay? Negative acceleration, because if you do not have a technical background or very good in mathematics, then it's difficult for you to understand what is negative acceleration. Negative acceleration means what? Deceleration. That's it. All right. So this is a typical example. Then you see the acceleration, deceleration, okay, with the positive value, negative value, positive value, negative value. Okay, quite straightforward. Then this is a video show you the an even distribution of the mass in the radial direction. Then it will also cause the vibration. Then again, this dynamic response also corresponds to alternating acceleration. Here, acceleration may take a positive value or negative value. All right, so we are not going to add in another term called the deceleration. All right, to make our description simpler. All right, okay. And then what should be the idea or equation of ideal vibration? Because it's like when we study the gas, we talk about ideal gas. Then in that way, we come out the equation of ideal gas. Okay, for the study of vibration, we can follow the same concept, okay, principle. Then what should be the equation of ideal vibration? So this video will help you to understand. All right.
Let's do a simple experiment. A simple experiment of spring mass system. This is a spring which is connected to a mass of 1 kg, and spring is having this much spring constant. And this blue dot line is the equilibrium point of spring. Means the point at which the spring force and gravitational force are equal. So what we are going to do here, we are stretching the spring by this much distance and we are releasing it. So you know, as you release the mass, it will go up and it will come back to the original position. And time required for this travel is known as time period. And in this experiment, we'll measure what's the time period of the system. We have a timer over here. So let's start the experiment. I'm releasing the mass. I'm measuring the time. It's going up. Touching the top position, now it's coming back. It says that the time period of the travel is around 6.28 seconds. Fine. Now we will do one more experiment. Same spring mass system. Here I am stretching it more. So one might be a gut feeling about time period. Will it increase? Will it decrease? You think it might increase because here the mass has to travel more distance compared to the first case. Anyway, let's do this experiment. We'll measure it. So it's going up as usual. Now it's coming back. And the time period of this oscillation is again 6.28 seconds. So this is the finding of the day. Time period doesn't change with stretch of the spring. It remains same for both the cases. And in vibration world, we commonly use a term called angular frequency omega, like this, 2 pi by time period. So experimentally, we have proved that frequency is a property of system. It doesn't depend upon user input or initial condition. Now the big question, what's the reason for that? Why time period remains same for both the cases? To find answer for this, we will do both the experiments simultaneously. So here both the mass are going up with a different amplitude and time period is same. And you can see the first spring mass system travels more distance, but at the same time it travels at a higher speed compared to the second case. So that's the reason. Even if the distance traveled by the first case is more than second case, it has got higher average speed compared to the second case. So both this effect get negated and time period or frequency of the system remains same. What about these systems? Is frequency of this bridge or electronic circuit, this glass or chimney again a property? Yes, you're right. This is again a property. You can define natural frequency for all these cases as you define Young's modulus or density. It's just a property. Now what we have done experimentally, we will do some mathematical analysis. So here is the case. Here my mass is at equilibrium point. I am stretching it and y is measured positive in this way. If you want to predict motion of any vibrating system, the only law you have to know is Newton's second law of motion. Mass into acceleration is equal to total force on mass. So you can represent mass into acceleration like d squared by dt squared is acceleration, mass is same. And here total force acting on the spring is only spring force, that is minus ky. Minus sign is over here because spring force is always in opposite direction of displacement. And you can solve this differential equation without much difficulty using some boundary condition, and this will be the solution. Displacement of mass varies like a cosine function with respect to time. And A is initial amplitude of the spring or initial stretch you have given. So graphically you can represent like this, a cosine wave. And you can find out this time period from this equation as this. Now let's see these equations more physically. This equation of motion. And according to this equation, my spring mass system will move like this. It will keep on oscillating. Here, what happens physically? The potential energy of spring getting converted into kinetic energy of mass. This energy is again given back to spring. So the energy transfer keep on happening. And
okay, so this should be good enough, all right? So from here, you immediately understand the equation of ideal vibration is a sine function, all right? And the frequency of vibration is one of the important parameter of this phenomenon, all right? And the amplitude is another important parameter for this vibration phenomenon, all right? So these are the two physical quantity we need to do the measurement or to use in order to do the computation, all right? And here you will see again, this is omega t channel. If let's say we write this as a sine omega t plus 90 degree, because cosine sine function, you can write them convert cosine function into a sine function, all right? So in general, we just call it as a sine function, all right? So this is omega. Then you will see omega only depends on the mass and the spring constant, all right? So it is independent, okay, from the initial condition of this vibration system, all right? So this is good enough for you to know, all right? So this should be the equation of ideal vibration of a single source, okay? So this is a single source of vibration. If you have a multiple source of vibration, then you must add them together, all right? Okay, so we move on. So then in this case, now you understand, if you want to do computation, if you want to do calculation, what should be the physical quantity on the computation or physical quantity on the measurement, all right? So the answer should be two. First one is related to omega. Then we know omega is also related to frequency. Omega equal to 2 pi f, okay? And the f is related to the period, okay? Then the period basically is a wavelength, all right? So this is one set of parameter which are related. So we just need to study one, good enough, right? Second one is amplitude, is this one. And sometimes we may talk about the average of the amplitude, root mean square of the amplitude, okay? By default, we just look at the peak value of amplitude. So therefore, we only have two independent quantity, okay, which describe sine function. Then in this case, which also describe the vibration signal. Clear, all right? Then this slide showing you what do we mean by angular speed? Okay, so these are the terminology you may encounter in literature, right? or is angular velocity or angular frequency, or sometimes people just use all these terms, all right? And for you, you just understand omega is equal to 2 pi f, right? So it's a quantity related to frequency related to period, because 1 over f is t, is a period. And 1 period is correspond to the wavelength, right? So all these are related, all right? Then, okay, here you see what is the period, okay? So because 1 over f is equal to the period, and the f equal to omega divided by 2 pi, because omega equal to 2 pi f, f equal to omega divided by 2 pi, then 1 over f is a 2 pi divided by omega, quite straightforward, all right? And this also equal to the wavelength of vibration signal, right? And then frequency, so you know, omega equal to 2 pi f, then f equal to omega divided by 2 pi, so it's quite straightforward, all right? Okay. And the amplitude, so is the coefficient in front of a sine function, all right? So this is the peak value, and obviously we can calculate what is the average value. If the signal is centered about the horizontal axis, then the mean value should be equal to 0, like in this case, okay? Mean value is 0, right? Then we can calculate what should be the root mean square. So root mean square is equal to a divided by square root 2. So we have seen this computation in the lecture about the measurement of voltage, and also in the lecture about the measurement of current, right? So you see the peak value divided by square root 2 is equal to root mean square value, all right? So these are quite basic mathematics behind the phenomenon of vibration. Then I have already mentioned to you, okay, vibration system in general is MIMO system. In particular, for special case, you may encounter vibration system, which is the SISO system. Okay, these are the terms used in control theory, but these terms are extremely simple and help us to immediately understand the nature of a system, all right? Because vibration comes from a system. So then we can talk about the vibration system. Then we should use this term SISO system, MIMO system, all right? So SISO means a single input, single output. So I guess all of you have studied this course like MA4822, which is about the control theory. In case if you did not study control theory, then this just for you to know, like conceptually it's not difficult. Single input, single output. Then we may have a multiple input, multiple output. All right, okay. So in most cases, vibration system is MIMO system. For example, inside the bus, right? So this is a driver inside the bus, okay? And this driver may receive vibration from multiple sources, from the engine, from the four wheel. The wheel has a suspension. The suspension produce vibration also, right? So at least there are 5 sources of vibration. So then the body of the driver, basically we capture signal like this. So this is the sum of these 5 sine function, all right? So then it is interesting for you to know how to analyze MIMO, all right? So then you see, because when we see a signal like this, then okay, for some of you, you may feel that it is a big headache to you to describe the nature of such signal. However, the good news is what? For those of you who have studied Fourier transform in year 1 mathematics or year 2 mathematics, then you will enjoy your study. What is the conclusion from a Fourier transform? Conclusion is what? All signal is a sum of a sine function. That's it. So this one is equal to the sum of a multiple sine function. For example, the bus driver receive a vibration signal. At least it is a sum of 5 vibration signal, and each individual vibration signal is a pure sine function. That's it. All right. So therefore, it's very important for you to leverage on this important knowledge in order to understand the content of today's lecture, because this lecture is very special, okay? It's not like other lecture, right? because vibration is a dynamic response, and the vibration is a system, and the vibration is MO system most likely. All right. Okay. So then we must leverage on this important knowledge and make your study enjoyable. All right. So any signal is a sum of a sine function. Then as long as you understand what is a sine function, then you can understand all signal. All right. So this animation basically showing you add in this four source of a vibration together, then you will be able to measure these kinds of a vibration signal from your sensor. Your sensor will output this type of time function, right? Then you should not be worried about the such signal. Then you say, I do not understand what is the nature of this signal. But actually, if you remember the conclusion from a Fourier transform, then immediately you know, this is just a sum of sine function. If you understand individual sine function, then basically you should be able to understand all signal in the physical world. All right. So in order to help you or help Rose with weak understanding about the Fourier transform or very weak understanding about the sine function, so I give you some video here just to build up your level of understanding about this important conclusion from Fourier transform, right? So this video basically will show you what is a Fourier series, what is Fourier transform, and what is the sine function.
Let us also create an axis that represents the angle theta. The green line rotates by the angle theta.
So here you can imagine the green line represents a vector, all right? So vector has a magnitude and the angle. The theta is an angle, or theta is an angle. Then the length of the green line is amplitude. So this is a graphic way to visualize A times sine omega t. Omega t is theta, right?
For each value of theta, the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta. The angle theta can range anywhere between negative infinity and positive infinity. This two-dimensional pattern is what we refer to as a sine wave. We can change the sine wave's amplitude. Phase, and frequency. Suppose we have two sine waves that are identical except for the fact that they have different amplitudes. If we add these two sine waves together, the result can be represented graphically as shown. Now, suppose that the two sine waves also have different phases. The sum of these two waveforms can be represented graphically like this. So long as the two sine waves have the same frequency, their sum will always be another sine wave of the exact same frequency, but with a different amplitude and phase. Now, suppose that the two sine waves also have a different frequency. If we add together sine waves of different frequencies, then the resultant waveform is no longer a sine wave. We can add together three sine waves.
Right, so this is half of the video. Then another half is here. Okay. So this video continue with
We
the
can add
previous video.
together four sine waves. We can add together five sine waves. In fact, we can add together an infinite number of sine waves. Here, by adding together an infinite number of sine waves, we have produced a pattern that looks like this.
Okay, this phenomenon is very interesting for you to understand. There is a famous statement in Buddhism, okay, which states that emptiness is fullness and the fullness is emptiness. All right. So from here, you see it is empty signal. It's just two level, all right? But actually, it's what is a fullness because this contain all the sine waveform, all right? Then fullness means all the sine waveform A together, then it become emptiness, all right? So then you see Buddha discovered this phenomenon more than 2,000 years ago. Okay, at that time there's no science, no mathematics. This will help you to think about this phenomenon. How come? Okay, we know this phenomenon more than 2,000 years ago. All right.
Now, let's add together a different set of sine waves. By adding an infinite number of sine waves, we have produced this other pattern that looks like this. As it turns out, every possible waveform and function in existence can be generated by just adding together different sets of sine waves.
So this is a very important conclusion.
In the two examples shown here, the sum of all the sine waves happened to be repeating waveforms.
All right. So then the question should be reversed. Give you any signal, which is the sum of finite number or infinite number of sine function. How to discover all these individual sine function? That should be the challenge. The good news is what? The good news is to apply Fourier transform. So this is why you see Fourier transform is extremely important in science and engineering. All right. Not only it helps us to understand the nature of any signal, but it offers us the tool to do this forward transformation, inverse transformation, and to discover the individual sine function inside any signal. So this is a very, very powerful mathematical tool and extremely important discovery in science and engineering. All right. Okay, so let's about the basic physics and the mathematics behind the phenomenon of a vibration. Now our focus is to know how to indirectly determine vibration signal and how to directly measure vibration signal. Okay, so we always start with the indirect way of determining vibration signal. And since vibration system is very, very special, all right, because in general, vibration system is an MIMO system. So this picture basically show you again, okay, vibration system which consists of a vibration source. So you see it's a multiple input, then multiple output, all right. Then for this phenomenon of a vibration, we may face two scenarios for the determination of vibration signal by computation. First scenario is we know the individual sign function, then what should be the final vibration signal? Then in this case, the solution should be straightforward because we treat individual vibration source as ideal vibration. Then we use a sign function to represent it. Then we have a multiple sign function. Then we just add them together, okay, by applying this sum of sign function, right? Then second scenario corresponds to the case if for whatever reason someone gives you a vibration signal, then how to discover the individual sign function? Just now I mentioned the magic tool is what? The magic tool is Fourier transform. All right, so then you see this is a very extremely important knowledge for you to know, and we are lucky that we have the Fourier transform. All right, so Fourier transform include forward transform and the inverse transform, and the inverse transform basically is for us to discover or to compute the individual sign function from the combined vibration signal, okay, or final or measured vibration signal, right? So in this case, we have a vibration signal, which is a time function. This could be the output from vibration sensor or vibration measurement and the sensing system, all right? Then how to discover the individual sign function, okay, inside this signal, right? The answer is to undertake this computation. Then in the case of having FT, which correspond to the vibration signal measured by sensor, then the output of this forward transformation will look like this. So you will see at the discrete location of a frequency, you see the peak value, peak response. So it means in this case, so this vibration signal is a combination of three sign function. Then the amplitude corresponds to the amplitude of the sign function. So you know the location of the frequency, amplitude of the signal. And on top of that, actually, we have another relationship, which is between the frequency and the phase. Okay, for simplicity, we just put the phase aside. Okay, so actually, this information is there. Okay, so you should not think that our phase is not determined by Fourier transform. It's not. Okay, so we have this time axis plus the phase. All right. So we have that information, but for simplicity of a study or explanation, so it is easier for us just focus on the frequency amplitude, right? Okay, so keep this in mind. So we are not going to make the description too complicated, otherwise you'll get confused, all right? So if we are able to determine amplitude, then we are able to determine phase, okay? So it's not the issue, all right? So here you will see omega equal to 2 pi f. And for those of you, if you know control theory, then you should know Laplace transform. Actually, Fourier transform is a special case of a Laplace transform. Okay, Laplace transform will use S vector. S vector equal to sigma plus j omega. If you consider the situation when sigma equal to 0, when sigma equal to 0, it means what? It is a steady state response in a system in which all the signal are sign function. Okay, when all the signal are sign function inside a system, then sigma equal to 0, right? So then we talk about the Fourier transform, right? So this is just for you to know. And physically, if you rewrite this equation in this form, here we apply Euler equation because natural exponential function raised to the power j omega t is equal to cosine omega t plus j sine omega t. Okay. So this is a very, very beautiful equation of Euler formula, right? So from here you will see, okay, this output actually will help you to understand the physical meaning, all right? So we do the integration over time. Then for every possible frequency, we calculate this one. Then this value will give a peak response if this frequency is contained inside the FT. So is this meaning? That means if this guy contains this frequency here, this frequency here, this frequency here, then this value will have a peak response. In case it does not contain sine function in other frequency. Also, you have a cosine omega t somewhere here, somewhere here. Then this integration gives us almost zero. You understand? So this is help you to understand the physical meaning, right? And then by applying forward Fourier transform, you will be able to get the frequency and the magnitude, and also frequency and the phase angle. Okay, so here I ignore the phase angle for simplicity of explanation. So it does not mean we cannot determine phase. All right. Okay, so I'm not going to repeat those similar mathematics. All right. So here basically show you, for example, let's say we have a single input pure sine function. So this is the input. You apply forward Laplace transform. Then you see this is a single output. It's a peak because this is a pure sine function. Second signal is to mix up this one. Okay, these two together, them together, then have this output. So this is a time domain function of the Laplace the Fourier transform. Then you see you only have a two peak response at these two frequency. All right. Then third situation, we these three sine function together, three. Then time function looks like this. Then we apply Fourier transform. Then you see we get the three peak response at the three location, okay, along the frequency axis, right? Then this example is to combine these four sine function together, them together. This is the result of combined, okay, sine function. So in time domain, apply Fourier transform, then you see we have a four peak response along the frequency axis. So this is the frequency axis. All right. So basically, this help you to understand this meaning. So that means this integration will only have a peak response if ft contain a pure sine function at the location of omega. That means for every possible omega, okay, those omega which are present inside the ft will produce a peak response. So this is magic mathematics, okay, magic result. All right, okay. But of course, if we know the frequency domain information, we can recover the time domain function. That is the inverse Laplace, inverse Fourier transform, right? And in the case of a vibration signal, in which we only have a finite number of sources, then in this case, the frequency signal is like a lot of a peak, okay? So then straightforward, you can apply this formula to do the inverse Fourier transform, all right? Because this is applicable to the case if we have a continuous function in frequency domain or continuous function of omega, then we must do integration. This is a discrete function in frequency domain. Then just use this one to determine the time domain function. All right, so it's quite straightforward. And here is the exercise just for you to know how to apply inverse Fourier transform. For example, we have a vibration sensor which output time function. Then we do Fourier transform. Then we get this result about the amplitude and the frequency. Now we ask you to determine, okay, the time domain function up to the detail about the amplitude and the frequency, okay? So here we just keep the field I unknown, okay? But actually the sensor will also output the information about the relationship between the phase angle and the frequency. Once you have that information, you just A in DI there, right? So it's quite straightforward, okay? So now you see, okay, so this is a solution for us to recover the vibration signal if we know the individual, okay, vibration signal, right? And interestingly, people, okay, discover this way to illustrate the physical meaning of a Fourier transform. I guess this will help you to understand, okay, the meaning of a Fourier transform. So in particular, it will help you to understand this important statement. Any signal is a sum of a pure sine function, right? So here, for example, you have a pure sine function, and you can, visualize it in the XY plane. For example, you calibrate X, Y in this way. So here is the value of F, then you times the sine 2 pi F, okay? So this F is another frequency variable, all right? So it has nothing to do with, this is original time signal. And this is, we scan through for every possible F to find out whether this F will trigger stronger response, okay, from this signal or not. Then you will see when this F is equal to the frequency contained by this FT, then you will see there's a strong response, all right? So this corresponds to my explanation here. So that means this one will have a stronger response when this omega is equal, okay, or is contained inside FT. That means original time function contain the sine function with this omega. Then at this location of omega, you have a stronger response, okay? So this observation is highlighted by this video, okay? I split this video into two parts. So this is the first part, and later on you will see the second part, all right?
This sound right here is a pure A, 440 beats per second. Meaning if you were to measure the air pressure right next to your headphones or your speaker as a function of time,
so this is the wave of the pressure
around its usual equilibrium in this wave, making 440 oscillations each second. A lower pitch note, like a D, has the same structure, just fewer beats per second. And when both of them are played at once, what do you think the resulting pressure versus time graph looks like? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually, which, let's face it, is kind of a complicated thing to think about. At some points, the peaks match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine wave. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. But right now, all it is a combination of 4 pure frequencies.
So on top is FT,
complicated,
right?
Given the low amount of information put into it. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sum. So our central question is going to be how you can take a signal like this and decompose it into the pure frequencies that make it up. Pretty interesting, right? Adding up those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple paint colors that have all been stirred up together. The general strategy is going to be to build for ourselves a mathematical machine that treats signals with a given frequency differently from how it treats other signals.
Okay, so this is a FT, this is a XY, okay? So this is a x-axis, a y-axis, okay? Then this, put them together, you have a vector, all right? So then we vary F, okay? So this F has nothing to do with the F here. So this is the F, okay, we scan through. So later on we'll see we have another F axis, okay? Then to find out what should be the value F will trigger peak response, all right? And immediately you understand, okay, when this F is contained by this signal, then it will trigger peak response. Okay, here is the time axis, all right? So, and also you will see the frequency, the period, okay? 1/T is the frequency, all right? So then within 1 second, we have a 3 peak. So basically a beat per second is what is frequency, right? That means have 3 oscillation per second. 3 oscillation per second means what? Frequency is 3 hertz, right? So this just help you to understand the meaning of all this join. Then immediately you will see, okay, when the F, that means we try all the possible F. When the F hits the value which is contained inside the FT, then you will see the peak response come out, right? So it's a very interesting discovery.
To start, consider simply taking a pure signal, say with a lowly 3 beats per second, so that we can plot it easily. And let's limit ourselves to looking at a finite portion of this graph. In this case, the portion between 0 seconds and 4.5 seconds. The key idea is going to be to take this graph and sort of wrap it up around a circle.
So this is XY plane.
Concretely, here's what I mean by that. Imagine a little rotating vector where at each point in time, its length is equal to the height of our graph for
Now you
that
see the
time.
vector in the
So
XY
high
plane.
points of the graph correspond to a greater distance from the origin, and low points end up closer to the origin. And right now, I'm drawing it in such a way that moving forward 2 seconds in time corresponds.
And the angle of this vector is equal to 2 pi ft. All right, so
to a single rotation around the circle. Our little vector drawing this wound up graph is rotating at half a cycle per second. So this is important. There are two different frequencies at play here. There's the frequency of our signal, which goes up and down 3 times.
So you see, this is the frequency of the inside the FT. FT may contain many frequency, okay? And then this is the frequency we try out, is this F, okay? So we try out that. Then when this, for every test frequency, like if this one contain inside the time function, then peak will appear, all right? So
per second. And then separately, there's the frequency with which we're wrapping the graph around the circle, which at the moment is half of a rotation per second. But we can adjust that second frequency however we want. Maybe we want to wrap it around faster.
So you see, we vary this one. That means to scan through all the possible value, okay, from 0 to infinity, for example, all right?
Or maybe we go and wrap it around slower.
Then you see when you reach 3,
and that choice of winding frequency determines what the wound up graph looks like. Some of the diagrams that come out of this can be pretty complicated, although they are very pretty. But it's important to keep in mind that all that's happening here is that we're wrapping the signal around a circle. The vertical lines that I'm drawing up top, by the way, are just a way to keep track of the distance on the original graph that corresponds to a full rotation around the circle. So lines spaced out by 1.5 seconds would mean it takes 1.5 seconds to make one full revolution. And at this point,
okay, so when we scan through this time axis, so basically is get the value here. That means we choose a value F, then we vary T, scan, then at each location of time, we get the value of amplitude. So that is this one. Then we can calculate XY, okay? Then for next T, we calculate XY. This why for every possible frequency F here, then we have a full curve, something like that, okay?
We might have some sort of vague sense that something special will happen
once you
when
reach
the
3
winding frequency matches the frequency of our signal, 3 beats per second. All of the high points of the graph happen on the right side of the circle, and all of the low points happen on the left. But how precisely can we take advantage? Then
we calculate the center of gravity. It's easier for you to see, okay? So the center of gravity, you see, will deviate from this point, origin. And if this one is not equal to this frequency, then you will see the center of gravity will be 0, all right? That means look at the indicator by center of gravity of this XY coordinate, all right? Then you see the peak response. It's easier, all right?
Advantage of that in our attempt to build a frequency unmixing machine. Well, imagine this graph is having some kind of mass to it, like a metal wire. This little dot is going to represent the center of mass of that wire. As we change the frequency and the graph winds up differently, that center of mass kind of wobbles around a bit. And for most of the winding frequencies, the peaks and the valleys are all spaced out around the circle in such a way that the center of mass stays pretty close to the origin. But when the winding frequency is the same as the frequency of our signal, in this case, 3 cycles per second, all of the peaks are on the right and all of the valleys are on the left. So the center of mass is unusually far to the right. Here, to capture this, let's draw some kind of plot that keeps track of where that center of mass is for each winding frequency. Of course, the center of mass is a 2.
Okay, so this is the first part of the video.
This
then we continue. Second part of the video
is relatively high. And then as you increase that winding frequency, and the graph balances out around the circle, the x-coordinate of that center of mass goes closer to 0, and it just kind of wobbles around a bit.
Once we frequency,
But
which
then,
is the
at 3
content.
beats per second, there's a spike
Right,
as
at T, then
everything
you see-
lines up to the right. This right here is the central construct. So let's sum up what we have so far. We have that original intensity versus time graph, and then we have the wound up version of that in some two-dimensional plane. And then, as a third thing, we have a plot for how the winding frequency influences the center of mass of that graph. And by the way, let's look back at those really low frequencies near zero. This big spike around zero in our new frequency plot just corresponds to the fact that the whole cosine wave is shifted up.
So this is
If
due
I
to
had chosen a
F0.
signal that oscillates around zero, dipping into negative values, then, as we play around with various winding frequencies, this plot of the winding frequency versus center of mass would only have a spike at the value of 3. But negative values are a little bit weird and messy to think about, especially for a first example. So let's just continue thinking in terms of the shifted up graph. I just want you to understand that that spike around zero only corresponds to the shift. Our main focus, as far as frequency decomposition is concerned, is that bump at 3. This whole plot is what I'll call the almost Fourier transform of the original signal. There's a couple small distinctions between this and the actual Fourier transform, which I'll get to in a couple minutes, but already you might be able to see how this machine lets us pick out the frequency of the signal. Just to play around with it a little bit more, take a different pure signal, let's say with a lower frequency of 2 beats per second, and do the same thing. Wind it around a circle. Imagine different potential winding frequencies, and as you do that, keep track of where the center of mass of that graph is, and then plot the x-coordinate of that center of mass as you adjust the winding frequency. Just like before, we get a spike when the winding frequency is the same as the signal frequency, which in this case is when it equals 2 cycles per second. But the real key point, the thing that makes this machine so delightful, is how it enables us to take a signal consisting of multiple frequencies and pick out what they are. Imagine taking the two signals we just looked at, the wave with 3 beats per second and the wave with 2 beats per second, and add them up. Like I said earlier, what you get is no longer a nice pure cosine wave, it's something a little more complicated. But imagine throwing this into our winding frequency machine. It is certainly the case that as you wrap this thing around, it looks a lot more complicated. You have this chaos and chaos and chaos and chaos, and then whoop, things seem to line up really nicely at 2 cycles per second. But as you continue on, it's more chaos, more chaos, more chaos, 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 chaos. Whoop, things nicely align again at 3 cycles per second. And like I said before, the wound up graph can look kind of busy and complicated, but all it is the relatively simple idea of wrapping the graph around a circle. It's just a more complicated graph and a pretty quick winding frequency. Now, what's going on here with the two different spikes is that if you were to take two signals and then apply this almost Fourier transform to each of them individually, and then add up the results, what you get is the same as if you first added up the signals and then applied this almost Fourier transform. And the attentive viewers among you might want to pause and ponder and convince yourself that what I just said is actually true.
Okay, this should be good enough for you to understand the beauty of a Fourier transform, all right? So if you have a time function, apply Fourier transform, then you can discover the individual sign function inside the vibration signal, all right? So this is a very, very important conclusion, all right?
It's relatively
result for you to know, all right? Now our main focus should be the direct measurement of a vibration signal, all right? Then what should be the working principle for us to follow? So actually there are many workable principles. And here I just highlight these 3 popular working principles for us to use. Okay, you should be good enough to guide your design or your future design of sensor and or measurement and the sensing system for vibration, right? Principle number 1 is to make use of this piezoelectric effect, all right? So when there's a vibration act on the piezoelectric material, then there's a DC voltage output, right? Then by converting DC voltage into readable value, then do the calibration, then eventually we should be able to know the amplitude, okay? To determine the amplitude, and then the frequency of vibration basically is equal to the frequency of the output signal. Because if let's say we only have a single source of a vibration, then output DC voltage should behave like a sine function, right? So this is the first principle. Second principle is something new to you because this is the first time in this course we encounter the use of AD current effect. Later on we are showing you. So AD current effect basically means when there is alternating magnetic field, okay? And when there is a conductive material or metallic material close to such a alternating magnetic field, then on the conductive material or metallic object, there is a loop of a current. So this is why we call it AD current. AD means it's a loop, okay, a circular movement, all right? So there's an AD current. And this AD current, because we know when there's a flow of a current inside the conductor, then this current will produce its own magnetic field. Then we can pick up this magnetic field, okay? Because this magnetic field depends on the relative position between the sensing coin and also the vibrating body. Assume here the vibrating body is a metallic body or is a conductive material, right? Then this is the way we can convert vibration into AC voltage. Then from AC voltage, we can convert it into DC voltage. Then we can use microcontroller to measure DC voltage, right? So this is the second principle, which is also popular in the industry, right? For example, we use AD current effect to design machine to detect the presence of metal. Okay, especially, you know, in the warm zone, we want to do demining. You understand this word, demining? So in the warm zone, so the instrument we use to detect the presence of a metal basically is based on the use of AD current effect principle, right? And in the airport, you see for security check-in, okay, you see there's a gantry to detect the presence of metallic part, okay, carry in our Bosch. So basically this gantry is a huge AD effect sensor, right? So then principle 3 is also popular to us because we can place seismic mass on the vibrating body, and then the seismic mass will change the beam, and when the beam deform or when the beam undergo periodic displacement, if we place a strain gauge on the beam, then the strain gauge will output periodic change in resistance, right? Then we should be able to convert resistance into voltage, right? Then this way we can measure vibration signal. So these are the 3 popular principles for us to follow, but of course there are other principles, all right? So then how to apply principle 1 in order to guide the design of a measurement and a sensing system for vibration? So you understand, okay, this principle is to convert vibration into periodic signal of a DC voltage. Then we apply microcontroller, okay, to do the conversion from analog value to digital one, okay? So here we leverage on this feature of a microcontroller, okay? So by now every one of you should understand that all microcontrollers are programmable digital sensor of DC voltage, right? So then you may want to know how to convert vibration into voltage. So we just apply this piezoelectric effect, right? So, and the piezoelectric effect allow us to design sensor and also allow us to synthesize vibration. For example, if let's say we have a periodically changing voltage applied to the piezo material, then this piezo material will undergo periodic vibration, all right? So at the beginning, we see the video how to make use of vibration to design a linear actuator, rotary actuator, okay? So basically, we follow this second property of piezoelectric effect. But here, we just apply the first property of the piezoelectric effect, right? So then in this way, okay, because vibration will basically produce a time function. Assume here we have a single source vibration, all right? So then in this case, we have a pure sine function like this, all right? So then the frequency of a vibration is equal to the frequency of the output voltage signal. Then the amplitude corresponds to the value or the peak value of voltage, etc. Right? So this is the solution for us to convert vibration into periodic signal of a DC voltage. And here we're showing you more illustration. For example, we may have this quartz crystal. So this is one type of piezoelectric material. Right? So if we compress the sensing element, then we have a voltage in this direction. If we decompress the sensing element, then we have a voltage in this direction. So this is why we get the theta V positive, theta V negative, all right? However, in the design of our circuit, we can make sure that the output voltage is equal to V0 plus theta V, right? So when theta V vary, so then this one will vary, all right? Okay. And this one show you an example of implementation. So you may want to know how to get this V0. So actually V0, you can A in here, okay? So this is the ground level, okay? Voltage at the ground level, same ground, all right? But here you see we get A in voltage here just to lift up the output signal. Then the piezoelectric material is here. So then you see here we'll have a voltage, here we'll have a voltage. So then you have a operational amplifier QA1, QA2, then these two output pass through again another amplifier. Then here you will see the time function for voltage, okay? Because this one is not constant because it's attached to the vibrating body. So then this one changing, then this is why we have a time function for voltage. Then this can fit into microcontroller. This is because microcontroller can take in the time function as an input because the microcontroller can run at a high frequency, all right? So it can do the conversion of every value, okay, within a very short period of time because microcontroller can operate these two operations. One is sampling. Sampling is just to take a sample at the discrete time instance, okay? Second operation is a quantization, convert that sampling the value into digital number. So all in real time, okay, very, very fast, all right? So it's not problem for us to enter a time function of a voltage into microcontroller, all right? And for vibration sensor, extra computation is a Fourier transform, all right? So because microcontroller will only give us a series of digital number which correspond to time function, okay? But we need to know what should be the parameter of individual sine function. Then we need to do Fourier transform. Then in this case, then we can discover all the peak value at the specific location of the frequency. Then we know magnitude, we know the frequency, and also we know the phase, right? Because the Fourier transform will also output phase angle, all right? Not just amplitude. But this display is just for simplicity purpose, okay, to simplify the explanation, all right? So phase angle is included inside the Fourier transform, all right? Then how to apply second principle to guide the design of a measurement and a sensing system for vibration? The second principle is to make use of AD, current effect. Then in this case, we have a vibration source, and the vibration source will add on the conductive material or metallic body. When metallic body vibrate, then we have AD current sensor, effect sensor, okay, at the proximity of this vibrating body. Then this vibration could be converted into AC voltage, okay, AC voltage. Because AD current effect sensor is more or less like a transformer. You can consider it as a dynamic transformer, all right? So the output, so the input is AC voltage, output is AC voltage, all right? And the output will be under the modulation by vibration. So that means inside here, the AD current effect sensor has a inner input AC voltage, all right? Then it produces AC voltage as output, but this AC voltage at the output is modulated by vibration, okay? Because the gap is changing. When the gap is changed, the output amplitude will change, all right? So once we have AC voltage, then we know that it is easier for us to convert AC voltage into DC voltage. Then we can use a microcontroller to digitize the time function of DC voltage, all right? So then what should be exactly the working principle of AD current effect sensor? So then you will see here, we have a sending coin. So this one will produce alternating magnetic field. Then you will see this is the inner power supply of AC voltage, okay? So this one has its own frequency. Then we should ignore this, the parameter, okay, of this signal, okay? Try not to confuse between the frequency of a vibration of this conductive body or metallic body with the frequency of applied AC voltage, all right? So here I use omega V. V means a vibration, okay? Nothing to do with this frequency here, all right? Okay, so we have a sending coin. So basically, it will produce alternating magnetic field. When this alternating magnetic field is in the proximity of a conductive material, then you will see we have AD current or loop current appear inside the surface of a metallic body. Then this loop current, so we know that when current pass through conductor, then it will produce its own magnetic field. We call it a secondary magnetic field or AD current effects magnetic field, okay? If we place another coin, we call it is a receiving coin. So this is a black color one, receiving coin, okay? Here nearby, then we should be able to produce voltage or current. So this is a principle of electricity generation. So that means we have a loop. When the magnetic flux vary inside the loop, then voltage will produce. It's like EMF, right? So electronic motive force, okay, EMF, right? So then this will output. Here the output is also AC voltage, okay? However, the magnitude of this AC voltage is a function of the distance between the vibrating body and this receiving coil, okay? So then this is correspond to the magnitude of vibration, but in this case, magnitude of a vibration correspond to what is the displacement. Then this displacement will be converted into the magnitude of output DC voltage, all right? So then we just need to get the time function of the magnitude of output DC voltage. Then this time function has a frequency. Then that frequency is omega V. You get it? Try not to confuse between the frequency of AC voltage and the frequency of a vibration, because we just need to know the amplitude or the displacement of this vibration. This one convert to the amplitude of current, AC current, and the amplitude of AC current is a time function. Then this time function itself has a frequency. Then that frequency corresponds to omega V. Get it? Okay. So this is slightly complicated because of the presence of AC at the input, AC at the output, because AC at the input has a frequency, AC at the output has a frequency, and then we say vibration body has a frequency, okay? Then vibration body's frequency is being captured by the time function of amplitude of output AC, right? So then is a time function of the amplitude of output AC will tell us the omega V, right? So, and then how to, once we know how to convert a vibration into the AC voltage at the output, all right? So the AC voltage at the output, right? So then we can, the next question is how to convert AC voltage into DC voltage. For example, then we can use this standard diode circuit coupled with capacitor. So capacitor is just for us to smooth out the output, DC output. So, and if we want to scale up and scale down the AC voltage and the magnitude, but sometimes the magnitude may be very small, then we can use a transformer to scale it up, or if it's too strong, we can scale it down. Okay, so and this illustration is for you to know that we scale down, okay, the magnitude. So this is the input AC before transformer. This is the output AC after transformer. Then this will pass through the diode bridge rectifier. Then we have a full half waveform. Then this pass through the capacitor. Then more or less we will obtain the smooth DC voltage as output. Okay, and when the magnitude A change, then this one will change. So this is why here then we have a time function of DC. Then from the time function of DC, and then we should be able to know the magnitude and the omega V. Okay, and here is the output from the. So this corresponds to the DC time function of a DC voltage. So this is the output after AC to DC conversion. So this is not the signal from this one. So it's after AC to DC conversion. So this is the output from the AC-DC conversion. Okay, so this more or less corresponds to the time function. This is the time function of DC voltage, right? And the that time function of a DC voltage should be the input to microcontroller. Then here is showing you example of a vibration sensor which making use of the eddy current effect. So here you will see, let's say we want to monitor the actual vibration of this motor shaft. So this is the shaft of the motor rotate, okay, and this is rotation. And due to vibration, then you may have actual vibration. Then in the proximity, we have this vibration sensor, and which make use of the eddy current effect. Okay, so then we have a sending coil and the receiving coil. The output from a receiving coil is AC voltage. Okay, so then after AC to DC conversion, then we have a DC voltage. Okay, time function. Then this is the input to microcontroller module. Then eventually we can output the digital, okay, value of DC voltage. Then this one eventually can pass through a module which will undertake a Fourier transform. Then you should be able to see the peak value, okay, at the frequency of vibration source, because each vibration source has its own frequency of a vibration. All right. So here's another physical product implementation. Okay, so similar to this one, then you see, okay, so this is a vibration body, all right. So this show you the physical implementation, and actually you can also learn the knowledge from this lecture to come out of your own design, etc. All right. Then how to apply principle 3 in order to design the measurement and the sensor system for vibration. Then this one is to place the strain gauge on the cantilever beam and place seismic, okay, mass at the one end of cantilever beam, and fix another end of cantilever beam. Then let the seismic mass, okay, to be attached on the vibrating body. So when the body vibrates, then the resistance value of the strain gauge will change, okay, change in a periodic way. So then the value will follow a periodic curve, okay. Then we should be able to convert resistance into voltage, right? Then we obtain the time function of a voltage, right? Then this time function of voltage could be converted into discrete time series of digital number, right? So this is a working principle. Then how to convert vibration into periodic change of resistance. So this is the design guideline. So you have seismic mass placed on vibrating body, and you have a cantilever beam. one end is connected to the seismic mass, another end is fixed on the ground, all right? So when this body vibrate, then you see we have a strain gauge here. Then it will make the strain gauge to change its value of resistance, all right? Then this change of the value of resistance could be further converted into voltage, all right? So, and how to convert resistance into the voltage, and in one of the previous lectures, we have already studied the way how to convert resistance into voltage. So I'm not going to repeat it again in this lecture, all right? So besides these three working principles, nothing prevents you to apply other design principle. For example, we can convert vibration into the change in capacitance, all right? So for example, in this case, we have inertial mass. When inertial mass move in the direction of a vibration, then the gap between the two parallel planes of capacitor will change. Then in this way, capacitance will change. Then we can convert vibration into capacitance and then capacitance into voltage. All right, okay, so then, okay, after the design of sensing module inside your measurement and the sensing system, always remember to do calibration. But for the measurement of vibration signal, calibration is slightly different, okay? Because we may supply, okay? Because vibration signal is for a single source vibration signal is a pure sine function, right? So normally the sensing element will reserve the frequency. So therefore the calibration is just to calibrate the amplitude A, right? Because this one we could treat as a time function, right? So then in this case, Xi represents the amplitude of vibration signal or reference vibration signal, all right? And V represents frequency of a reference vibration signal, okay? So if we know this reference, then we get the Y, then we need to find the equation of which relate Z to X so that the output the Z is exactly equal to input the X, and the X here refer to the amplitude, okay? Because the sensor element will preserve the frequency, all right? So at the input side, okay, you see A basically equal to X is a time function, okay? Because during the calibration, you can put the, let's say, a vibration signal with the same frequency, but the different amplitude, right? So then you see how we have the response from your sensor, right? Then at the output side, so basically this corresponds to Z, okay? So this some special attention for you to know, right? Then after calibration, then you can do some testing, okay? To let you supply single source vibration signal to your sensor, then you repeatedly to read the output, then you let's say you do the reading for 100 times, 200 times, then therefore you can calibrate the mean value for amplitude, repeatability, accuracy for the amplitude, and also to see whether there is a hysteresis effect or not. Okay, in this case, you can increase the amplitude of vibration signal at the input, then reduce the amplitude of vibration signal at the input, then you do the comparison to see whether there's a difference between the error or not. All right, so this is just a standard procedure for you to follow. Okay, so that's all for the study of this lecture. So the key takeaway from this lecture is for you to understand the basic physics behind vibration. And by now you understand that the vibration is a dynamic response from a vibration system, which could be produced by rigid body or by gas or by liquid, etc. And most importantly, we have studied the mathematics behind vibration, in particular, the beauty of Fourier transform, because Fourier transform allow us to discover individual, okay, equation of a single source vibration from the measured vibration signal, right? So then the second key takeaway is for us to know, okay, how to do computation, okay, in order to determine the key parameter inside vibration signal, and in particular, we have a study 3 design principles for us to follow in order to guide the design of a measurement and the sensing system for vibration. Thank you for your attention. I'm looking forward to seeing you in the study of the next lecture.